So, quiz one. Oh, my good old favorite student. A force of 767 newtons is needed to push a car across a lot. Two students push the car 28 meters. How much work is done? So our original definition of work was force times distance. We did say, Matt, that the force and the distance had to be in the same direction. I think they are. You're pushing horizontally. The distance is horizontally. So I think it's just going to be 767 times 28 Newton meters. 767 times 28. 21,470. I'm going to go 21,500. 21,476, but really it should be the 2 sig figs because 28 has 2 sig figs. Whatever, I'm not going to be too fussy. Joules, or I guess technically Newton meters is what a joule is, but joule, we call that a joule. 1 mark. Suppose they complete this task in 58 seconds. Suppose they do. How much power will they generate? Well, power is work over time, which was, now I'll use my exact value, 21,476 divided by 58. And I get 370 watts of power. 370 joules per second, which we defined as a watt. What? Watt. 1 mark. 1 mark. 2A. What work is done by a forklift raising a box 2.8 meters? Well, work is force times distance. They didn't give me the force. Well, they did. Raising, lifting. We assume your force that you're doing work against is gravity. Any luck yet, Elijah? Yep. Okay. There's the force, mg, times 2.8. In fact, really what you're finding is the potential energy, because that's how much work you did. We said that work was the change in potential plus the change in kinetics, so that also works. 688 times 9.8 times 2.8. I get, I'm going to go 18900. Well, for those of you who really like to be accurate, 18,879, which is going to be 18. Or really, I should go to 2 sig figs. That, but I'm not being fussy on sig figs. But for what it's worth, that would be correct. Suppose it does this in 73 seconds. How much power? So same as before. Power is work over time, which was 18879 divided by 73. This number divided by 73, I doubt this will work out evenly, 258.6. I'm going to go 259 watts. Technically 260 watts because it's 3 sig figs. Is work a vector or scalar? Scalar. Work is measured in what units? Joules. It's actually a Newton meter, and we defined that as a joule. Power is measured in what units? What? What? Okay. Joules per second, which we called a watt. Then we turn the page. What is the minimum power generated by a 64 kilogram person who climbs 82 stairs? Each stair has a height of 21 centimeters in 83 seconds. Well, power is work over time. Work is going to be force times distance over time. mgh over time, because I think we're doing vertical work, which means you're doing work against gravity. What's the mass? 64. G, 9.8. What's the height? Well, it's 82 stairs times each stair has a height of 0.21 meters. That's my total height. Divided by 83 seconds. I think this will get me there. 64 times 9.8 times 82 times 0.21 divided by 83. 130 watts, is that right? Going once, going twice? Yeah, people nodding. Matt says yes. 130 watts. Why'd you write minimum power, Mr. Dewick? Well, that's assuming that all of the energy is conserved and goes into nothing but raising the heights. Oh, probably some went into heat because you get hotter when you climb stairs. Sound, all sorts of stuff. So minimum power, 130 watts, probably more. An electric motor lifts a 25 kilogram load a vertical distance of 24 meters in 32 seconds. Power is work over time. And that's going to be mgh over time, because once again we are lifting. Mass 25, G 9.8. Just keep in mind on your test, I may give you, Tara, the mass in kilograms. I may give you the weight in newtons, in which case don't multiply by 9.8. I already did that for you because I gave you mg, not just m. So read the questions very, very carefully. Height 24 meters, 32 seconds. 25 times 9.8 times 24 divided by 32. You get 183.75, 184, let's call that. 183.75, which is technically actually 180 if I go to 2 sig figs, which is all the data that I have. Units, power. What? You'd think after 10 years I'd be tired of that joke, but no. Supposing the motor draws 244 watts of power, how efficient is it? So that symbol for efficiency is that funky thing, although if you just write EFF, I'll clue in. And Nate, we said this. If you're not sure what, it's always the smaller number divided by the bigger number, as long as they're both watts or both joules, or make sure the units match. So it looks like I have 183.75. That's the power I'm getting out divided by, but it looks like the motor is drawing 244 watts in. Times 100%. How efficient is this motor? That divided by 244 times 100%. 75.3% efficient. Number 8, a 65 Newton force is horizontally applied to a mass of 12 kilograms sitting on a level floor for a distance of 14 meters. How much work did the applied force do? Well, work applied is going to be force applied times distance. It's going to be 65 newtons times 14. Going to be 910 joules of work. Now that's the total work that the applied force did. Not all of that went into the mass, making it speed up. Some of that went into heating up the floor. How much? Well, it says if there is a coefficient of friction of 0.25, how much work does friction do? I better draw a little free body diagram. I got mg down, normal force. It does say the floor is level, so there's the applied. There's friction. I guess I would say work done by friction is going to be the force of friction times distance. Friction is mu times the normal force. I don't know the normal force. Oh, but look, 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 look. I know another force the same size as the normal force. Mu mg times distance. 0.25. Mass 12. G 9.8. Distance 14. 411.6. Is that right? Now, if you called it negative, I'm good with that. If you didn't, I'm good with that as long as you did part C right. Technically, you're losing energy because you're in the opposite direction. And then what we're saying is, what's the net work done? Well, the net work is how much the applied force did take away what we lost due to friction. $498.4. Or if you go to, how many sig figs, Mr. Dewick? Technically 2. If you said, well, 500 if you went to 2 sig figs. 498.4 joules. Sean, that's the energy that went into making this mass speed up as you're pushing it. In fact, if I knew you started from rest, I now know that you gained that much kinetic energy. I can figure out your final velocity because work is also change in kinetic energy plus change in potential. My last day's lesson, which was sneaking in some physics 12 using the work energy theorem. Okay, and work energy theorem is not really going to be on your test, so don't freak out about that. I didn't give you actual exercises or homework for that. What was this quiz out of? Was it 1 mark each? I think it was 1 mark per question, wasn't it? Did I say I need 2 marks anywhere? No. Can you give yourself a score, please, at the top of the page out of 13? Any lawyering with me? Now is the time. Yo. So last day, you may recall, we looked at what I called the work energy theorem. Now, I'm not going to put questions involving the work energy theorem on your test. In other words, this whole concept of work being the change in potential plus the change in kinetic. I'm not going to be asking you specific stuff like that, very, very difficult stuff like that, although it's good to keep in your back pocket because there are some questions on your test that you can choose to answer using this or using other methods. Okay? Your test is going to be a week from today, so it's going to be next week, Tuesday. All right? What do you have right now? Well, your first bit of homework is to finish quiz number 2. This is going to be on most of the law of conservation of energy stuff. So we have work, power, kinetic energy on number 4. Number 5 has potential energy. And we have some conservation of energy. Then I've given you 2 great big reviews. The first one is called Unit 4 Review, Work and Energy. There's my high-tech topic for it, title for it. I put, because I was, for some reason, feeling fairly merciful, or actually I think another teacher typed this up and I stole this from them. Here's kind of a rough summary of what we've done so far. I did include the work energy theorem there in case you choose to use that to answer some of these questions. So your homework on this page, let's see. 1 is good. You know what? I think that's all good. Yep. 11 is good. 12, here's an example of a graph question. Some of you were asking, will there be any graph questions on your test? Probably 1. So here's an example of how you can handle that. Good. Tarzan, power, units. I think I had the test in front of me as I was going through this. So there's some nice questions here for you to do, and I think you guys have the answers attached or not? Oh, they're in brackets. Yeah, so you guys have the answer. Like, you guys have the answers? Okay, that's that one. That one, every question is fair game. Then I gave you a work energy concepts review. That's this one. This one you want to focus because some of these questions, this is actually from the American curriculum and they do things in a bit different order. But I like a lot of the conceptual stuff here and I like the little cartoony things. Some of these we're going to skip. Specifically, I think you can nuke 4A, 4B, actually, I think 4B you can keep. I apologize. How much work? Sure, that would be vertical. You don't need the 6. They're just trying to confuse you. You're lifting at a vertical distance. All ramps below. 5 is good. You can discuss with your classmates or not, but 5 is good. So let's circle the ones that I am circling. 1, 2, 3, 4. Skip A, I guess, Mr. Dewick. 6 is good. 7 is good. 8 is good. You can skip 9. Yoink. One is good. Please make sure that you, actually you don't need to change things to kilometers per hour because they didn't give you the mass. If you double the speed, how much more kinetic energy do you have? Twice as much? Huh? 4 times. Okay, that's I think what they're trying to get you here. Double it 4 times as much, triple it 9 times as much. By the way, that's why the difference, if you're ever in a car accident at 20 kilometers an hour versus 80 kilometers an hour, 80 kilometers an hour, 4 times bigger speed, 16 times more damage. That's why those ones are fatal. Also, my message is, as you're getting your licenses, slow down. There's no need to be in a rush to get anywhere. Leave 2 minutes early, and you won't be late for class. I mean, you won't be late for wherever you're trying to get to. So 1 is good, I think, except sure, that were, yeah, I think all those are fair game. Yep. This is the one I think I want to nuke. Number 2, where it has the pulley. Let me see. Woman supports the spring scale readings that show. Yeah, we can nuke number 2. We can also nuke number 3. This is where we don't look at multiple string pulleys here in the Physics 11 curriculum. 4 is fair game. So that's also good. When's your test? A week from today? When will I do a tutorial? Well, probably somewhat Thursday during class. This is due the day of the, what's due next class is your quiz, take-home quiz number 2. The reviews are all due a week from today. Good question. They're due on the day of the test. Okay? So if you're looking for a good summary of everything, here you go. This is also a chance to get completely caught up. My report cards are due next week. I'm probably going to be doing your report cards this weekend. I may try, if we all do really, really good on this next test, I may try and get this next test on your report cards. Oh, that would mean I have to redo them all Wednesday or Thursday night, and everybody would have to be here. Anyways, I might. I don't know if I'll quite make this test on these report cards or not. Okay?